Hi everyone, Steph here from Old Guy Melts Plastic. Recently I recorded a video that ruffled a few feathers and may have caused a bit of consternation amongst my viewers. I do apologize for the video presentation coming off the way it did. That was not my intention. The video in question, I was demonstrating the print quality differences between a couple of Voron Design Cubes that I had printed with different print settings. And the difference in print settings resulted in a roughly 40% reduction in the total print time. So a number of viewers commented that the video itself was not really all that useful if I didn't actually provide concrete numbers of what I changed to achieve that result, and I don't disagree. The goal of my video content on this channel has always been to try and be educational and helpful. So given those viewers' comments, I decided to follow up with this video where I'm going to be reviewing my V2 Voron V2 configuration. We'll talk about the hardware setup and also about the software setup that I've got using Clipper and Mainsail, the various configuration options in there. And then we'll look at the slicer settings where I did most of the work in tuning for the faster speeds. So by the end of this video, you should have all the information necessary to conduct your own performance tuning for your printer. So I want to be clear here. Taking my numerical values and my settings, my config settings and slicer settings, and just plugging them into your own printer is not recommended. I have modified my hardware somewhat. If you have, from a hardware perspective, if you've done everything that I've done and added and upgraded all the components the way I have, then in theory, yes, we should be able to achieve the same results and by just plugging in the numbers. But there's no substitute for conducting your own testing to see what works for you. I am not a perfectionist. I'd like to say I am a good enough-ist, like as in that's good enough for me. That's not perfection, but it's good enough for me. So because I am a good enough-ist, I often settle for maybe subpar results that other people would say, hey, that's not sufficient. We can do better. But you tune your printer to your requirements. This video will necessarily be a longer video because there's a fair amount of material to go through. I'm not going to step you through every test. I will show you where to go about, reading more to conduct your own testing. And hopefully by the end of this video, you'll be armed with all the information you need to properly tune your printer to the best of its abilities. All right, so with all of that out of the way, let's dive right in. So a little bit about my printer, and I'm not going to do a video, overview of all the mods that I've installed, but let's just go over some of the basics. It is a Voron V2 350 millimeter build. That was originally purchased as a form-bought kit online, and I've since modified it a little bit by replacing the hot end, for example. I have updated, so I'm now running, let's talk about the hot end. I'm now running with a Rapido UHF Plus from Thetis. The Rapido UHF Plus is equipped with a PT1000 thermistor, and it is paired with a Bondtech CHT 0.4 millimeter Volcano nozzle. So with that tool head, I am able to achieve somewhere in the vicinity of about a 44 cubic millimeter per second maximum flow rate. And I say somewhere in that vicinity because I haven't myself done any flow rate testing. I am basing that number on other people's testing results and relying that with the same hardware, I should be able to achieve, good quality prints with those same numbers. So we'll talk more about that in a minute. In addition to the hot end, I've also upgraded the A and B motors, specifically that drive the X and Y axes, to LDO 2504 speed power motors. Mine are the AC variety, not the heat, not the not the variety for heated chambers. So they run fairly well. I'm running them relatively conservatively with not a ridiculously high run current. There's probably room for improvement there, but I found I was able to achieve pretty good speeds and accelerations, at least as I mentioned, good enough for me, um, without having to push them too far or run them with too high of a current. So we'll look at that in just a moment. They are powered by a 48 volt power supply through my Octopus Max Easy primary MCU. So I have two power supplies that are connected to my Octopus Max, the typical Meanwell LRS 224 power supply that drives the main board and most of the logic and other accessories on the printer. And then I have a Meanwell LRS 148, which is only driving the A and B motors. All of the Z motors are Moons motors, and the Moons motors are still powered at 24 volts by the 24 volt PSU. Okay, so with that hardware out of the way, let's look at the software configuration that I have, and you can compare against what you've got set up in your own environment. So logging into my printer in Mainsail, I'm going to go into the machine menu here and then find the printer.cfg. There's a lot of other CFG files in here. I like to keep some parts of my configuration modular and separate in their own CFG files and then just include them in the printer CFG. So that's how I like to segregate the information and the configurations. So you'll see a lot of include statements at the top of my CFG, but my printer CFGs, but you do whatever works better for you. Some people prefer to have all the configuration in a single file, and if that is more appealing to you, then by all means make this work for yourself. Moving right along. So I am running a CAN bus toolhead. I do have the primary MCU, and again, this is an Octopus Max Easy running Easy 5160 stepper drivers. And those stepper drivers are capable of higher voltages and higher run currents, and also are powered at 48 volts for the A and B motors. So this is the Octopus Max Easy here. This is a Big Tree Tech EBB36, which is my toolhead MCU, and it is running on CAN bus. I've changed my printer configuration here to increase the max velocity from 200 to 600 and the max excel from 2000 to 15,000. These 200 and 2000 numbers are, the default stock profile that you'll find on the Voron Design webpage for the Octopus. And I've updated a little bit here based on the testing results that I've done. We'll talk more about those testing results in a bit. The max velocity, I haven't really changed a bit. I think the default for this is 15. I have increased it somewhat. On a V2 printer, the Z-axis doesn't move very fast typically. It's only incrementing slowly with each print layer. So there's not a need to push it excessively fast, and I just leave these values fairly low. In general, most of my configuration settings are what I would deem pretty conservative. I'm not looking to, compete with the likes of 24/7 printing or VES 3D with their speed benches and their 1500 millimeter a second print times or print accelerations and speeds. So I'm still looking for, a high quality part, but I'm trying to shave off some of the print time from the total experience here. So again, my values work for me in my hardware. Don't go just copying and pasting my values into your config. I'll talk more about how I got to these values in a moment. Let's keep looking at my configuration. So my X and Y steppers are configured with nothing unusual. They're 16 microsteps. They are 1.8 degree stepper motors, so they are configured with 200 full steps per rotation. I have my homing speed set at 50, but that just affects homing. It doesn't really impact anything else. The Stepper X and Stepper Y drivers, again, are both running at 48 volts on easy 5160 drivers. As such, I've set the run current on these to 1.1, and there is definitely some room for change here. I would say this run current for 48 volt drivers is still on the conservative side. I could increase it, but I'm getting decent results as is, and I may push these values higher at some point in order to maybe unlock some higher accelerations and or print speeds, but for now, this is good enough for me. The sense resistor here for these motors or these 5160 drivers is different from the typical TMC 2209 drivers. You might see that your configuration has a different sense resistor value, and that's dependent on the driver that you're operating. So take that into account if you're looking to update your configuration based on these values. I do run the X and Y steppers and the Z steppers, for the Z motors for that matter, with interpolation enabled and stealth chop threshold disabled. So, but again, you can change these according to your requirements and decide what works for you. The Z motors on the V2, there's 4 Z motors, and they're all configured pretty much the same. On my configuration, the Z motors are still running on TMC 5160 steppers. However, these 4 TMC 5160 steppers are powered by the 24 volt power supply. So consequently, I have not bumped up the run current on them. They're just at the default of 0.8. But I have changed the sense resistor because they are still on a TMC 5160 driver. And again, stealth chop threshold is disabled and interpolate is enabled. So all 4 Z motors are configured that same way. So we'll skip right ahead. For the extruder configuration, it is in my case, the extruder is a Annex Engineering Sherpa Mini that has been modified with a Ridga gear reverse drive gear. And the Sherpa uses the Bondtech gearing system, so it's still a 5-to-1 gear ratio, just like it would be on, say, a stealth burner. Uses the same gear ratio and same rotation distance. I haven't modified these values at all. I did do some testing, and I was getting with extrusion measurements, asking for 100 millimeters extruded. I was seeing 99.9 millimeters, like it was right close to 100. So I just left these values per the stock values. I did not change them in any way, shape, or form. I'm still using microstep 16 here. And 200 full steps per rotation, so none of that has changed. I am running camp, and with the Voron purge in camp, the recommendation is to set max extrude cross section to 5, which is a fairly high value, but it is needed to allow that Voron purge, that Voron logo purge, to work properly with camp, which is the Clipper adaptive mesh and purge. The EBB36 toolhead PCB that I'm running on this extruder is equipped with a Max 31865 chip, which allows me to connect the PT1000 thermistor that's on the Rapido UHF Plus. And so it's configured here with these values. I have set a max temp for this printer of 300. I don't tend to print with higher temperature filaments, so 300 is plenty for my requirements. The only other thing to note here for the extruder on the EBB36, the stepper driver is a TMC 2209, and I am running it with a run current of 0.6. It is a pancake stepper motor, and I do have Stealth Chop threshold set to 99999 here. And that is because through conversations on the Voron Discord, I've been, led to understand that the value of Stealth Chop is it reduces the noise of the motor, the noise of the stepper driver and motor attached to it, at the cost of decreasing the possible speed potential of the motor. But for the extruder, the motor isn't operating at ridiculously high speeds. So there's no real need to worry about that speed decrease. And the other benefit of enabling Stealth Chop on the extruder is Stealth Chop in general provides the motor with more torque. So while it does impact the overall speed of the motor, it increases the torque, which gives the extruder motor more pushing capacity to push the filament through the nozzle and into the hot end. So for that reason, I have enabled the Stealth Chop threshold here just on the extruder motor, and so this value of 9999 represents that. I still have interpolate true here, so that counterbalances the relatively low microsteps. From a performance perspective, that's pretty much it. Everything else in here is going to be related to motion and fan control. So from a purely print performance perspective, the rest of the configuration is not really relevant. I will share my configuration in the description of the video below, or a link to where I've updated or posted my updated configuration on my GitHub page. So feel free to reference that if you wish. But again, don't take my values and just blindly plug them into your printer without comparing our hardware configs, without doing your own testing for your own printer and your own assembly. So how did I get to these numbers? Well, I stood on the shoulders of giants. And by that, I mean, I looked at what other people had done before me, and a great starting point for anyone that's building their own 3D printer or even using a pre-made 3D printer. If you buy an off-the-shelf 3D printer and it requires minimal assembly to get you up and running, there's still great value in referring to Andrew Ellis's print tuning guide. And again, I'll share the link in the description of the video below. So with regards to print performance, I mean, I strongly recommend that everyone take the time to go through this guide from start to finish, read everything that Andrew's put down here on the site, and learn from it and use the information here to apply it to your own configurations and see how you can improve your own print performance and print quality. Andrew's advice is very good, and it is, for the most part, equally applicable regardless of the type of 3D printer you're using. It's designed for filament printers specifically, so specifically FDM printers versus resin printers. But all of his advice here, I think, is very, very well laid out and equally applicable to pretty much any printer out there. So with regards to the performance tuning that I did, I'll show you where I started, and you can take my advice and run with it and make it work for you. In my situation, I started by looking at Andrew's own super slicer profiles that he shared here. And you can go to his site and click on the here link, and it will take you to his GitHub page where his profiles are shared out for everyone to look at and consume. Again, read through what Andrew's done here and understand what changes you're bringing to your printer before you do that. But this is a good starting point. Andrew's profiles are, again, well tuned for a good quality print. They may not necessarily be configured for optimal performance as far as print times is concerned, but they do end up giving you a, in my experience at least, they've ended up giving me a very stable, good quality print 100% of the time. And as such, even though I've gone past this and tweaked my own settings for my own needs, I will still keep Andrew's stock profiles loaded in my slicer software in order to use as a backstop or a check to make sure that if I change something and something goes sideways, I can always default back to Andrew Ellis's configurations and be relatively confident that I'll still get a good quality part out of it. So the super slicer profiles is an excellent starting point, but we can go beyond. And so what I'm going to recommend next is to look at your printer's motion system. So anything to do with the movement of the tool head and the gantry, for those with printers that have these concepts. And what Andrew has put together here is a test speed macro, which I've imported and used in my own printer. And I use the test speed macro to first find the maximum speed at which I can move my tool head. And then once I've found the maximum speed using the test speed macro, I then look at increasing the accels slowly until I find my maximum safe acceleration. And these values are going to vary from printer to printer. Different geometries of printers, whether it's like a Delta printer, Cartesian, or a Core XY printer, are going to behave differently. So again, you need to run these macros and do these tuning settings on your printer and find the numbers that work for you. However, I was able to settle on what we saw earlier in my configuration was the max velocity of 600 millimeters a second and a max accel of 15,000 millimeters per second squared for the movement of the tool head. So using this test speed macro, you're going to try slowly incrementing speeds and accels until you get to a pair of values that work well for you. Make your tool head move a little bit faster, but don't shake your printer apart. So I would recommend increasing these values by small increments, maybe increase the speeds by 25, 50, 100 at a time, backing down as needed if you find that the print head starts to move too fast. So the other thing that I'll mention about my configuration is a lot of people are moving to sensorless homing for their DIY printers specifically. I am using still physical microswitch end stops for X and Y. So the results that I get out of the test speed macro are good for my configuration. The test speed macro does give less reliable or accurate results. Basically, the results are not necessarily as trustworthy from the numbers perspective if you are running sensorless homing. And by that, I mean, when you look at the test speed macro, and if you read through the document here that Andrew Ellis has shared with us, you can look at the output of the results and compare them, and it's in this block here. If you look at these numbers on a system with microswitch end stops, and these numbers don't vary by more than a full step, then you can be relatively confident that no skipping of the motors has occurred. But in a sensorless homing configuration, that may not necessarily be true. You might still experience no skipping, but these numbers might be outside of the range of a full step of motion. So be aware of that if you are running sensorless homing. You can still use the macros to test your speeds and visually confirm that everything is working well and listen for any motor skipping. And that's still valid, but you should not necessarily rely on this numerical analysis to confirm whether or not any skipping has occurred if you're running sensorless homing. All right, so this was, for me, a couple of hours of repeated iterative testing, slowly increasing the speed, slowly increasing the XLs, and then arriving at the values that you saw in my printer config of 600 and 15,000. And again, I would say for my hardware, these values are still maybe a bit on the conservative side. I know some people have pushed theirs significantly further, but they work for me and it's sufficient for my needs. So you decide what level of speed you're willing to accept and what your hardware can push, and then set it accordingly for your requirements. All right, so next in tuning for print quality and print speeds is something that I personally have not gone through determining the maximum volumetric flow rate in a from a testing perspective. I have, rather than go through this testing myself, I have simply relied on the numbers that Andrew Ellis has presented here, based on the fact that I have, the same hot end that he's listing on this page. And so we can look here and see, that the flow rate does in fact relate to print speed based on values that you set in the slicer. We'll get more into my slicer settings in a minute. So these approximate values are based on the commonly available tool heads, particularly for Voron printers, but really for most 3D printers across the board. And so in my specific example, I am running a Rapido UHF, and my Rapido UHF has a CHT nozzle. So previously on this list, there was a specific value listed for Rapido UHF with a CHT nozzle. He does mention the Bondtech CHT nozzle down here, and it was 44 cubic millimeters per second for that hardware combination for the hot end. So I took that value at face value and am using it, I guess, more or less blindly, which I recommend that you'd not do. But I have been getting pretty good results so far with that value of 44 cubic millimeters per second for my hot end configuration. But you look at what hot end you have installed on your printer and then match the flow rate accordingly based on this table, or take the time and do your own flow rate testing per the pinned instructions here. Okay, so with the flow rates, now you have known values for your max speed and accelerations, and also a starting point at least for your maximum flow rate, whether you're using the numbers from this table, or whether you've actually gone and tested your own flow rate specifically by extruding some filament and seeing what kind of results you get. Armed with those 3 bits of information, we're ready to look at the slicer configuration and see what we can do to tune that up there. All right, so let's go right into, and I'm using the latest version of Super Slicer. Or sorry, not Super Slicer, my apologies, Prusa Slicer. So this is the 2.6 release of Prusa Slicer. And what I've done here is I've opened 2 instances of Prusa Slicer. On the left, I've got the Andrew Ellis PIF standard 44 cubic millimeters per second flow rate profile for print settings, filament, and printer. And on the right, I've got my tweaked and modified profile. These are my daily driver profiles for those things. I have preloaded a Voron Design Cube just as an example print. Realize that your performance gains that you get for your prints are not going to be flat across the board for every print. They will vary significantly based on what part or parts you are printing on any given plate of prints. So just caveat there. Don't expect a flat performance increase across everything. It will vary significantly based on the parts that you've loaded in. However, this is a fairly common part that people use for testing their printers and print quality. So I decided to load it in and see what we get. With Andrew Ellis's config, about the only thing that I've tweaked out of this config, I've kept all of his stock values, except I don't print with a skirt or brim unless specific parts need it. So by default, I've got my skirt and brim disabled. So I've gone ahead and done that in the print settings under skirt and brim. I simply have set the loops to 0 and set brim type to no brim. Other than that, these configuration settings are right out of the profiles that Andrew Ellis shared on his GitHub. So just a caution there. If you print with brims or skirts normally, then obviously your results will vary a bit from mine. I like to start with the physical limitations of the printer. So we're going to go right into the printer settings, and I'll open up the same screen on both. And those physical limitations are set. I call them physical limitations. They're what you set in the software, but to me, they're based on the quantitative testing results that I got from the speed testing and so on and so forth. So in Andrew Ellis's profile, we have the maximum feed rates. He has them set to 450. I've bumped mine up to 600. So that's a 33% gain. And then I did not change the Z values here. So those I've just left alone. In Andrew Ellis's profile on the left, he has this maximum accelerations at 10,000 for X, Y, E, and acceleration when extruding. I've bumped mine up to 15,000, again, based on the test speed macro tests results that I've gotten. And the Z doesn't change here. The Z doesn't change, and the acceleration when retracting I haven't changed. I've left alone. I've also not modified any of the jerk settings, so they're all at default values. Let's look at filament next, because it'll be relatively short compared to the print settings where there's a little bit more meat. So for filament, if we look at Andrew's profile and my profile and compare things, I have not modified the extrusion multiplier. I did originally do some extrusion multiplier testing on my own, but I came to realize that for me, the default values that are in Andrew Ellis's profile are in fact good enough. They might not be perfect, but they're close enough for the material that I print with, and the material I tend to print with the most often is Sparkle ABS Plus in various colors that I order from Sparta3D.ca. So thank you to the folks at Sparta3D.ca for supplying that filament. I like that filament. It prints well for me, and so I've tuned this profile specifically for that filament. If you print with different filaments, other types of ABS, ASA, PLA, PETG, obviously these values might change for you, particularly the temperatures based on that. But for me, the EM of 0.924 from Andrew Ellis's profile is fine, and I've left it alone. The density value is just used to calculate the weight of the filament used, the weight of the part. So if you change that, I haven't done any testing to confirm the density value of the filament that I print with, but I've just left that alone. It's informational rather than performance impacting, so I haven't touched it. Similarly with the cost and spool weight and so on and so forth. What I have changed here, however, are the temperatures that I print with. So for ABS, 250 is commonly used as a default print temperature for ABS. I have increased mine a bit to 270 in order to allow for a little bit more liquid filament in the nozzle, hopefully increasing the flow rate somewhat. Next, we'll look at cooling. So by default in Ellis's profile, the fan speed is set to 50% with a maximum of 100%. I've bumped that up to 75%, again with a maximum of 100%. I have enabled dynamic fan speeds. I haven't really done any, specific tuning around that. I got these values based on recommendations from other people. In particular, a shout out to a Voron Discord user named Dirty Kitty Litter. Dirty Kitty Litter and I have had some good conversations recently around, the printers and tuning and upgrading and modding the printers. And he himself got some assistance from other users on the Voron Discord, Shifting Tech and others, and always, basing a lot of our information on the profiles that Andrew Ellis has shared. So thank you to all of those people and all the community members on the Voron Discord community for being so forthcoming with all of their information and so helpful whenever I run into problems that need troubleshooting. So the takeaway here is I've increased the fan speeds. I've also increased the dynamic, or set the dynamic fan speed so it can modify the fan speed based on the overlaps. And these so far have been working really well for me with these settings. Cooling thresholds. So one thing that is directly, speed impacting as far as the total print time is concerned is this value of, basically forcing each layer to take a minimum time value of 15 seconds approximately. So what this value does is, if a part or plate of parts, if a given layer would take less than 15 seconds, it slows the tool head down and extrusion down so that it will, spend at least 15 seconds on that layer, allowing the plastic time to cool. And while this is absolutely important with the materials to know about, based on the materials that you're printing with, it does necessarily mean that you're slowing print speeds down. So you might find that decreasing this value improves your print speed or print times, reduces your print times, but it might have a negative impact on particularly small parts or small areas, as it doesn't allow those small areas time enough to cool before laying down more hot molten plastic on top. So for the types of parts that I'm printing, I might tweak this value for a given print if I know that there's going to be smaller parts like that and bump this value up. But by default, I've set it to 0. And so that's not necessarily, the best solution, but it's working for me. It does, in fact, help to reduce the print time significantly. but it can result occasionally in a part that has some little melty bits that you might not want. So maybe try tweaking it down from 15 to 10 seconds or even 5 seconds. In my case, I have set it to 0, and I will, like I said, tweak this value up if I know that I'm going to be printing parts with a lot of small, fine details. Then I'll do that. And then everything else is the same. So I haven't added any additional changes here as a filament type, filament overrides, nothing else unusual here. This is all default values. Note that on the advanced tab here, I have not set max volumetric speed. I'm not controlling it through the filament. In theory, you could have a default volumetric speed in your print settings and then override it here per filament if you wanted to do that. I'm not doing that in my case, but that is an option for you as well. Right along, let's go to the print settings and have a look. So again, we're looking at kind of default PIF standard values here for all of the layering and perimeters and horizontal shells, etc. I haven't tweaked those values at all. They're all pretty much standard and the same. For the PIF standard, the recommendation is to use 40% fill density or infill density, and I've kept that. Fill pattern is completely subjective. Some fill patterns do print faster and some fill patterns print slower. I use grid or triangles interchangeably for most of my prints. Sometimes, honeycomb print or honeycomb infill or gyroid are also quite common, but I tend to stick to either grid or triangles for my parts. I'll be honest, the length of the infill anchor and maximum length of the infill anchor values I acquired through Dirty Kitty Litter's profile that he shared with me. I have not done any specific tuning around this or intentionally changed this. This is just picked up from somebody else's shared profiles. So it does vary from what you see in Andrew Ellis's here. I'm not sure the impact of these all told, so be aware of that. Other than that, everything else here is the same. Skirt and brim, again, I'm not running with a skirt and brim. By default, I run my parts without supports generated, although when I do, I tend to use organic supports, and I'll enable this as needed for the part that I'm printing. So speed is where we get into things a little bit here. By default, the different types of features, I guess, the different print features on a part are often printed at different speeds to improve your part print quality. And so based on my testing and the testing of other people in the community, I've increased some of the speed values and acceleration values again for my printer. You should check and see what works well for you in your configuration. And then based on the test values and all of your various test results, slowly try changing some of these values. Now, specifically, all of my visible features and my low speed features originally in the Andrew Ellis profile, those features are printed at 30 millimeters per second. So that would be small perimeters, that would be gap fill, and the first layer speed. I've bumped those up in my configuration to 80 millimeters per second. So small perimeters, again, for gap fills actually at 100, and then the first layer speed's also at 80. Obviously perimeters, I've doubled the value here. So, you can look at these. The ones that you're most concerned with for the visual quality of the print would probably be external perimeters, as well as your top solid infill and your first layer speed. So if you wanted to print those a little slower to, hopefully improve your print quality, you might do that. But again, these are the values that I've found work for me, and we'll compare the print times difference here. Because my speed has been set to 600, that's what I use for my travel speed, my default travel speed, and that's in there. Looking at the accelerations, although as we saw in my machine limits and in my printer config, I have the max accel at 15,000. I'm not using that for print controls. So I am going even a little bit below that and more conservatively in my print profile here. So those values, the maximum travel values for accelerations are 12,500 rather than 15,000. So I'm never actually pushing my printer to those extreme limits. And again, my values are fairly conservative. So, you can, you needed to change that. All right, so let's go ahead and save that profile. Yeah, my values are fairly conservative, and you'll find that you might be able to push your printer even faster if you don't mind the noise and vibration that the printer makes. So with that, the other thing to look at would be the Advanced tab, and here's where, again, I took Andrew Ellis's defaults for extrusion widths and applied them in here. In Andrew Ellis's profiles, these are set as percentages in Super Slicer. Prusa Slicer handles these width values slightly differently, and so I've converted them from percentages to static values or fixed values instead. But they represent the same ratios that Andrew Ellis had in his original profile as well. So let's have a look and see what this change does, right? We've seen the differences between my profile and Andrew Ellis's profile, and let's look at what that gives us from a print time perspective. So with this Voron Design Cube in Andrew Ellis's profile, I've sliced it, and it's estimating the print time to be approximately 57 minutes. And in the legend here, we can see a breakdown of how much time and filament is going to be used for each of the various features of the print in question. And then first layer approximate time is 51 seconds and a total time of 57 minutes. When I slice the same part in my profile, now, to be fair, I am getting some warnings about possible print stability issues. So, take that into account. And if you feel that's of a concern to you, you can click on more and find out what it's complaining about, and then potentially go and tweak some settings accordingly. But I have, achieved an estimated printing time here of 35 minutes. And, these are the values that I used to print those two cubes, or at least, I used Ellis's values to print the slow cube and my values to print the fast cube. And those are the, the cubes that you saw in the other video, or you can go look at the other video and see the results. Are they identical? No. Are they close enough that maybe it doesn't matter for a functional part? I think so. And just by estimates alone, I'm saving not quite 40%, but close to 40%. We'll call it 38 or 39% of the print time for what I would consider to be fairly closely even parts. If you're looking at filament used, or by length or volume, you can see that this profile does consume a fair bit less filament. I haven't really dived into why that is. Probably one or more of my settings are causing it to extrude less filament for a given feature. But from my perspective, the faster part in this case is in fact good enough. And again, your results may vary for your printer. and the materials you use and the hot end you're using and the motors you're using. But by understanding the different features of your printer and testing their values to see how far you're comfortable pushing your printer, you could potentially save yourself a fair amount of time on the prints that you get out of it. So that's it for this video. I hope this was a little bit more informative than the previous video, which some people accused me of being a bit clickbaity, and they were not wrong. I'm not complaining. That was not the intent of my video. I do try to be informative and educational in these videos. I hope that this content was useful to you. And again, please, do your own testing. This will be a slow process. Don't expect it to work if you just take all of the values that you've seen in this video and plug them into your own configuration. You should absolutely run your own tests and see what limits you can push your machines to. But there's still lots of room for improvement, I think. And finding what level of part quality versus print performance, what ratio of those you're willing to accept and tolerate on your own builds. So once again, this video has gone on a bit longer than expected. Thank you for watching, and I hope to see your comments in the video below. Bye for now.